So our motivating example for this is a company is going to manufacture bags of potato chips, and they advertise that they contain 50 grams of chips. We know that there's some natural variation in the weights of the potato chips in the bags. It would be entirely impossible for the machine to be able to get it at exactly 50 grams every time. You know, you can't have someone sitting back there breaking off the little pieces of chips until it's exactly perfect, right? We know there's going to be some natural variation, but they're advertising it's 50 grams. So on average, there should be 50 grams of potato chips in that bag. Now, I don't know about you, but sometimes when I grab a bag of potato chips, I open it up and it looks like there's a lot of air in there and not as many potato chips as I'd like. So seems like there's just not enough potato chips in there. And so one thing that could be happening, we don't know this for sure, but we have this hypothesis that maybe the company is actually underfilling the bags, right? Maybe they're only putting 47 grams of chips in there on average, and they're just hoping no one notices. Or it might just have happened by random chance that we happened to get a few of the bags in a row that were less filled up, but we don't really know. So what we can do is we can gather some data to try to test this hypothesis. Okay, so we randomly sample 40 bags and we weigh them. The sample mean is 49.75 grams. So that's not too far off from the 50 grams, but you know, the sample mean is definitely less than the 50 grams. We know that the machine that they use to fill these bags, it will always fill the bags with a standard deviation of 0.5 grams. So that's our sigma, right? So in this case here, we know what sigma is. All right, so sigma is 0.5, okay? And then this 49.75, that's a mean that came for our sample. So our symbol that we used for that was X bar. Okay. Now what we're gonna do is we're gonna give the company the benefit of the doubt. And we're gonna say, benefit of the doubt, let's say they really are filling the bags to the 50 grams on average that they should. So we're gonna assume that mu is 50. And we're gonna work out the probability that we observe a sample mean of 49.75 grams or smaller. So this is similar to maybe one of the problems that you would have seen on assignment 3. But what I'm gonna do, because we're interested in the probability of observing a sample mean, I'm gonna draw a distribution of the sample mean. And the distribution of the sample mean followed that central limit theorem that we just talked about in the last video, right? So X bar here is gonna follow this distribution. It's always gonna have the mean mu, and it's gonna have the standard deviation of X bar is gonna be sigma over the square root of n. Okay, so in this particular case, we're going to assume that they truly are filling the bags, right? That was this statement here. We're gonna assume that they really are filling the bags to 50 grams, right? So that means that we can plug in, this mu is going to be 50 here, okay? And for sigma over the square root of n, we're gonna end up with sigma was the 0.5. Now n here was the sample size, and our sample size here was 40 bags. So that's our n, so that's what we're gonna plug in. So we've got the square root of 40. And that'll give you some number, okay? But this here is the distribution of the sample mean. And what we're gonna put on is we wanna know the probability of observing the sample mean of 49.75 or smaller. I don't know exactly where to draw the 49.75, but I know it's definitely gonna be to the left of the mean, just for our sort of theoretical diagram here. So I'm gonna draw 49.75. That's an observed sample mean, and they asked us for the probability of 49.75 or less. So that means that we need to get this area in here, anything to the left of 49.75. Okay. We would have talked in class about how if we have a value to get an area or a probability. So one option is to try to convert this into a z-score. We could do that, or we could just use p-norm directly, okay? So we can go and use p-norm in R, right? So this is what I would type into R. The p-norm is going to be the value, which in this case was the 49.75. And then we put in the mean of the distribution, which in this case is 50, and the standard deviation, which in this case was 0.5 divided by the square root of 40. That's how we type it into R, okay? So let me just show you how to plug that into R. So here we are in the R console. So if it was me, I would probably just type this command directly into the console here. So I've got p-norm of 49.75, mean is equal to 50, and standard deviation is equal to 0.5 divided by the square root of 40. Okay, and that's going to spit out some answer. That's the probability there. So I'll borrow that for later. The other option, if you like working in the chunks, in any chunk here, you can plug in that same, plug in that same code into any chunk you want and press play to run that chunk, and it should spit out the answer right in there. So if you prefer working in the R Markdown sheets, you can, but usually in this case, when I'm using a calculator, I just plug it directly into R. So now that we've sort of run that code in R, we were able to get an answer here. We worked this out. This was 0.00, yeah, I'm gonna have to look it back up in R what it was. Come here, R. 0.00307827, okay? And so this here, that's the probability of observing a sample mean of 49.75 or smaller, given that the true population mean really is 50. So maybe I'll write that in words for you. So from there, this sort of leads me to the next part of this is we've observed a really, really small probability there, right? So even if I converted that to a percent, that's way less than 1%, right? So there's a couple of things that could be happening here. We definitely could be sort of observing a rare event. Rare events happen, rarely, but they do, so that's possible. We could have just by random chance happened to grab some bags that were particularly small. Or another thing that could be happening here is that our assumption, our original assumption that the true mean is actually 50 could be wrong. So I think I wrote this out here. There's sort of two different things that could be going on here. So when we get this really, really small probability, it's sort of telling us, that's usually when we sort of say, well, let's maybe reject this initial assumption and say, wow, that probability is so small, I can't believe it.